So we're happy to have Favero.
So I'm going to take you back in time to May 13th. You can be with Earl. So this is a talk about joint work with Matt Ballard and Ludmil Kachikov. So Ludmil gave a talk yesterday, and actually, sorry, that's from a different paper. So this is more work with Ludmil. Okay, and now it's on the archive. Okay, so the basic motivation was work of Toby Dickerhoff and Dima Orlov. So first, theorem of Dickerhoff. If you have f and f prime isolated singularities, and you consider the category of matrix factorization associated to these polynomials, then you can have a model for basically the product of these categories as DG categories, which is just you tensor the two rings and you take the differences of potentials or sum the potentials. So this is the sign is just a convention for this is functors between the categories, and this is the tensor product of the categories. Okay, so in other words, the functors between matrix factorizations can be realized as another category of matrix factorization. So that. So this is a reminder of what a semi-orthogonal decomposition of a triangulated category is. It's basically a way of decomposing a category so that morphisms only go in one direction. So you have this sequence of categories, and morphisms only go this way. There's no Hans this way. And every object then has a functorial way of decomposing into objects in the space. Okay, so this is the theorem of Orlov. Is that there's a comparison between categories of matrix factorization and derived categories of coherent sheaves on spaces. Basically, in the case of a hypersurface and projective space, when you're Fano, then this category of matrix factorizations is a sort of a full subcategory of the category here, or in other words, a semi-orthogonal component. When you're Calabi-Yau, it's an equivalence, and then it reverses when you become general type. You have so what I mean here by K is the residue field has a realization, the stabilization of the residue field in the matrix factorization, and so you have this, the matrix factorization together with some number of graded shifts of it, and then you have the category as a component of the matrix factorization category. So it flips around. Okay, so the question that we tried to answer in this paper is what is the analog of Dickerhoff's result in the case of graded matrix factorizations? And so then you can use Orlov's theorem to sort of compare what does this mean, right, in terms of geometry. Because we know that if you have two categories of spaces, then there's a nice geometric model for the product, which is the product of the space. Okay. So the theorem is you take M and M, so M and M prime, so you have two rings, you have two grading groups, and you have two homogeneous potentials, okay, satisfying some support condition. And when you want to take, so So then the theorem is really similar to Toby's theorem. You just tensor the rings. So what's the category of functors between these categories of now graded matrix factorizations? That's the only difference, is that these rings are now graded and these potentials are homogeneous. Well, it's the same thing. You tensor the rings, you take the difference of the potentials, and now the grading group is sort of the interesting part. You sum the two grading groups, and you set D equal to minus D prime, essentially. So D comma 0 equal to 0 comma D prime. Yeah? So what is that doing? That's just the minimal relation to make this potential homogeneous.
What do you mean an element of D? What does that mean?
Sorry?
F is an element of D?
So yeah, this is notation. This is just F is in the Jacobian ring. So that the Turina algebra equals what's going on. So that's the very
Yeah.
So independently, so we should say that Polishchuk and Van Droop have also proven this, and so we posted joint with them a couple weeks ago. They posted at the same time, and so they prove it in the case where the singularities are isolated and the abelian groups are rank 1. So some corollaries. Okay, so you can you can compute Hochschild homology using this model for the functor category. And what you get, so Toby did this when you did, so Dickerhoff did this when you do the non-graded case, right? And so, what he got was the Jacobian ring, right? And so what we get is some, invariant Jacobian ring summed over some pieces, but I don't really have a lot of time, so I don't really want to explain the details, but there's a way of computing Hochschild homology. And, I'm going to skip ahead. So to get that, because I want to get to some examples. Okay? So, the first thing you want to do is, since this grading group changes, so I want to compare this model for the functor category with some geometric decomposition like Orlov. So technically Orlov states it for Z-graded rings, but you actually take, so if you have Z by Z mod 3 comma 5 or something like that, that's Z again, but 3 comma minus 3, that's some Z with some torsion, right? So you want to just broaden his result to that context, but that takes absolutely no work. You just follow his proof verbatim by closing under this action of the torsion group. Just everything take orbits under the torsion group. And so that's what this statement is. M is some finitely generated abelian group of rank 1. Okay? Then here, okay, so I haven't told you what everything is because I skipped it. You tensor product the rings, you get some affine space, but M is now some grading on each of the pieces, some more complicated grading. So this is really some weighted projective space with the grading by torsion group rank 1. and you sum the potentials, right? And so you get a stack from that data, right? You take the zero set of this, and then you mod out by this. You take the global quotient stack defined by this, by the dual group to this graded group, and then what happens is, well, you can take this. There's a parameter associated to this, and so in essentially the Fano case, you get the matrix factorization component once again as a quotient, as a piece, and then you get the orbit of the structure sheets here under the action of the torsion group. So before in Orlov's decomposition, we just had the different structure sheets, right, by the Gornstein parameter. But now we just have those closed under the orbit of the torsion group. And what's this A? Well, this A is the product of all these categories. Okay, so that's how we set it up. Okay. Second, there's an equivalence between this stack and the product. So, in other words, this product can be realized as a stack in the Calabi-Yau case, okay? Or it can be realized as a component of some stack when this parameter ends up being positive, and otherwise this product has this stack as a component when this parameter. Okay. So let's go to some examples.
How do you know it's a stack? I mean, you're giving a description of the derived category of it. How do you know if there's any stack instruction? What do you mean it's a stack? Like in the previous slide.
So you define a stack, right? So you have some potential, and you have some affine space, and you have some group action.
You want out in this stack.
You just take the global quotient stack to the zero set by the dual group to the gradient. And that's the stack. And so that's what naturally happens when you the point was that the grading group was altered, right? So you get some more complicated grading on your product, and so you just take a stack, and then you do Orlov's theorem for the stack. And so you get a comparison of the point is that you get a comparison between the product category and some component of a stack, or maybe some equivalence with some derived category of a stack. Okay? So it's easy to do it in examples. This is the AP minus 1 singularity, AQ minus 1 singularity, and the AR minus 1 singularity. Right? We tensor those three together, we get the sum. Right? But what sum? Well, the stack you actually get is it's the stack defined by the sum of these three things, with this grading group, which is classically the grading group of the weighted projective line, DQI. Okay? So that's just like the simplest stack you could get from doing this. Okay? And what you get is that this weighted projective line really is just a product of three AN quivers. Yeah? Okay. And so, I mean, the weighted projective lines have these classical drawings. Maybe I'll just stick here since it's a little time. So you have the weight p minus 1 number of these guys. Then you have q minus 1 of these and r minus 1 of these. Okay, and then so the quiver looks like this. Okay, and so this quiver will either be a component of the product of these squivers, or vice versa, this product will be a component of this quiver, or they'll be mutations of one another, depending on your parameters. So I have some examples here. Okay? So let's take 2, 3, 5. Okay? So that's A1 by A2 by A5. So A2 by A5. Should be A4, that's a typo, yeah? Okay? And when you compute what this Gornstein parameter is, it's 1. So I actually have this written incorrectly. So this actually is a mutation of the AA quiver. Okay? And then when you kill one, you get the E8 quiver. And then when you kill one, you get the mutation of the E7 quiver. So I guess I'm out of time. But yeah, the basic point is that you can enhance this matrix factorization category to the graded case, and then you get all these geometric pictures. But I think that's about right now. Yeah. Questions?
So what is the Gornstein parameter? What is it?
You want to know exactly? Okay. So yeah, I shouldn't have skipped this maybe. So you have a collection of hypersurfaces and polynomials and coordinate rings of these hypersurfaces, and so you take the free z to the s, right, the product of them all, and then I had this relation, so I have to set each of the degrees equal to each other. So this is my grading group, and then did I say what the Gornstein parameter is on this? Okay, so what it is what's the Gornstein parameter for this weighted projective stack? It's just the sum of the basis guys, okay? And then you have to subtract by adjunction, you have to subtract the degree of the potential. So that is this, except they're all equal, right? So you just choose T1, E1. So the Gornstein parameter is something like E1 plus En minus T1, E1. But these are all the same. So
geometrically, it's what the degree of the nth canonical bundle, right?
okay.
So it's just telling you how positive and negative the nth canonical bundle is.
Yeah, so it's basically Dano, Flaviao, or Dano type are the three cases there. Although that's not precisely correct anymore.